welcome to the last day. And I see a lot of you are sort of struggling to get in this morning. But in any case, we will make a start. So just to be clear, this is the tutorial, segment routing, right? Being a tutorial, I try and take it a little bit easy because I try not to assume too much prior knowledge. Because it's, we've got 90 minutes, so we've got time to actually go through material in a bit more detail than we would otherwise. But one of the things that I would like to do before I get started normally is to get an understanding of the, the audience. So one question and only one question. How many of, well, sorry, I shouldn't say that because no one can count how many. So can you put your hand up if you are familiar with MPLS? So about, a few people, right? Good. Because segment routing, requires some knowledge of MPLS. It's a way of making MPLS great again, right? So we'll talk about that. Now, for those of you who are not familiar with MPLS, do not worry, because I spent about 20-30 minutes of the tutorial trying to bring you up to speed with MPLS. Because if you do not have that knowledge, the rest of it will not make too much sense. In terms of questions, if you have a quick question, I will take it during the tutorial. Okay? If it needs a detailed explanation, we'll leave it till the end. But in any case, raise your hand and we'll give you an opportunity to ask any questions you have. Okay, so in terms of the agenda, a few different things. I've got a lot of material and I do not expect to complete all of it. All right, so we'll keep going until the clock runs out and then we'll stop. The slides are there, so you can take them away, read them. If you have questions, come back to me. The important thing is that whatever we do end up covering, you understand it well. Okay, so we'll look at segment routing in a nutshell. I'll give a quick introduction to MPLS. We'll look at segment routing from the perspective of some use cases. We'll go into the architecture if time permits, and at the end we'll talk about the MPLS data plane in a bit more detail. Okay, so very quickly, what exactly is segment routing? So segment routing is actually a new paradigm for routing. We know that in IP networks, the way we do routing is it's destination based, right? You put a destination address on an IP packet, every router along the way examines that destination, makes a lookup decision on what is the next hop to send it to, what is the next interface to send it over. With segment routing, that changes. It changes because the path that is taken by the packet is now dictated by information that is contained within the packet. Information that is put there by the source. So the source of the packet determines how the packet should be routed in the network, as opposed to the destination address in the packet. Now this is a very significant change, right? This is not how we understand normal routing to be. There are reasons why we do this, and they will become clear as we go along. So I've already talked about this. It does it by encoding within the packet information. This information is referred to as segments. Each segment is some sort of topological information. The segment that is encoded in the packet could indicate the next node to send it to, or the next interface to send it over, right? So it's giving some pretty detailed information about how to route the packet. It's assuming that the network does not know that itself. The reason we do it is to reduce the amount of state in the network. Once again, that'll become clear once you look at some examples. The second reason we do that is that it allows centralized computation of paths. So this segment routing paradigm is quite key to a lot of SDN deployments, because as you know, in an SDN deployment, what we're doing is we're actually delegating some control plane functions to a central controller. So having a central controller that has visibility of the entire network means that it can make more optimal decisions that it can pass down to the network, to the routers, which they can then use as paths within the network. So that's what segment routing is, right? 3 things. So keep that in mind. Even if you don't understand the rest of the presentation because I've gone too fast or there's too much material, the thing you've got to take out of this is that it's a new routing paradigm. It uses source routing. The source puts information in the packet itself that dictates how the packet should be routed. Difference to current IP routing and MPLS forwarding is that the current model of forwarding is based on the destination address. So it's talking about where the packet needs to get to, not how. Whereas in segment routing, we are telling the network how to route the packet. Why do we use this? We use it for central computation to optimize routing decisions. Okay, so that is, in a nutshell, segment routing. If you're left now, you still have enough to be able to talk about it in an intelligent way, but I suggest you stick around for the rest of it. Okay, so an introduction to MPLS, very quickly. So when I put the slides together, I intended that I would do this in half an hour. Now that we've already used like 10 minutes, so I'll try and finish this in 20 minutes, really quick. So please keep up. If you cannot, or if you cannot understand anything, let me know, right? It's okay if you go over half an hour, as long as you understand what we're trying to get to. Okay, so MPLS, a lot of words here. What MPLS actually means is, or it stands for, is multi-protocol label switching. Now it's a switching mechanism that was invented about 20 years ago. So it's not new, right? It's been around for a long time. It's become mature. The whole concept of MPLS is to put a label in front of a network layer packet, such as an IP packet. And instead of using the IP header information to route the packet, we use the MPLS label to switch the packet. The whole idea of doing that was to make it simpler, because IP routing requires a longest prefix lookup, as you all know. And that is a somewhat non-deterministic process, because it depends on the contents of a routing table, and so the performance you get may or may not be the same for different packets. With MPLS, what we're actually doing is we're doing an exact match lookup, because it's a single label. It's a 20-bit label. So by doing that, we're able to get deterministic performance. But that's not really the reason we do it now. We do it today because it is also a nice tunneling technology. By putting an MPLS label on a packet, you're telling the network where that packet needs to go. And we can do some pretty interesting things with it. So I will go into some detail on that. So the MPLS label, where does it go, right? So if you look at a IP packet here, you see you have a payload, some sort of transport protocol, TCP, UDP, and then you've got your data link layer encapsulation, Ethernet or PPP or whatever it is. What we do in MPLS is the packet comes in to a node that is called a label edge router, the LER. So the LER sits between the non-MPLS domain and the MPLS domain. So whatever comes into it leaves it with an MPLS label, right? Simple as that. So in this case, a packet comes in, an IP packet. What the LER does is that it puts an MPLS shim header in there, right? So MPLS is not really an encapsulation. It's just putting a shim header in there. It doesn't encapsulate the entire packet with a new encapsulation, but it does put this header in. It's a bit like a VLAN tag, right? When you put a .1q header in there. So this MPLS shim header has a few fields. One of them is the label. Don't worry about the rest of them for now. Not really relevant for our discussion. So it puts a label in there, and this label is just a number, right? This is not like an IP address, although an IP address is just a number as well when you think about it. But we normally think of this as just a number between 0 and 1048575. So about roughly a million labels that we have to play with. Okay, there are some operations that we do with MPLS labels that are important, that you need to understand. So the first operation is what we call a push operation. So go back to the previous slide. What did we do? A packet came in, an IP packet. It did not have a label. The LER, the label edge router, puts an MPLS label between the IP header and the transport, or the data link layer header, sorry. That operation of putting a new label on a packet or putting a new MPLS label on a packet is called a push operation. Now, as the packet travels through the network, subsequent hops in the MPLS network do a swap operation. They swap it for another label so that the number of labels does not actually change as a result of a swap operation. It gets to the end of the network, the edge, the other edge of the network, where it leaves the MPLS domain. So there we have a node called an egress label edge router. That strips the label. That's called a pop operation. So it's really pretty simple. Push, swap, pop across the network. All right? There are a few MPLS tables. Once again, a bit of terminology here, right? Just like, you know, when you learn a new technology, you have to sort of embrace some terms and so on. The one that I'd like you to pay attention to is the one in the middle, which is called an incoming label map. What that does is it is really the forwarding information that is used by our router. So when a packet comes in, it looks at it, looks at the incoming label map, and looks at what label came in. And based on that, it works out what label to swap it for, or what operation to perform on it. The operation could be a swap, it could be a pop, right? It'll all become clear with an example, as my, I guess, attendees from the SDN workshop know. So quickly, what does an MPLS network look like? There are two types of nodes. I already mentioned one of them, which is the label edge router. There are two types of label edge routers. There's one that is at the ingress of the network, and there's one that is at the, or one or more, at the egress of the network, in this case. And obviously, when a packet goes in the other direction, the roles swap, right? So here we have a path through an MPLS network. Packet comes in to the ingress LER. What is the operation it does on the packet? Push, pop, or swap? Anyone? Push, right. It does a push. You now have a label. It gets to the LSR. LSR stands for Label Switch Router. So the difference between an LER and an LSR is that with an LSR, you're receiving labeled packets, you're sending out labeled packets as well, right? So it's in the core of the MPLS domain. So in this case here, the packet already has a label, comes into the LSR swaps it for another label. And it keeps doing that until it gets to the egress LER. At the egress LER, we strip the label. That operation is called a pop. That's right. So it does a pop at that point. So you guys are all MPLS experts now. So that's a good start. We'll go into more detail so you become even more proficient at this. Okay. That was a generic sort of MPLS network. We also have the concept of a MPLS virtual private network, right? In an MPLS virtual private network, we essentially use the term provider edge to refer to an LER, right? It's the same kind of thing. You have unlabeled packets coming in, and you're putting a label on it. But just so that, you know, if you do come across this terminology, they're kind of used interchangeably, but technically speaking, the PE and P terms are VPN terms. So PE, whoops, how do I go back here? PE is referred to, is a LER. The P is an LSR. Okay, so one of the major applications of MPLS is to build virtual private networks, and these virtual private networks can carry many types of traffic. It could be IP traffic, It could be Ethernet traffic. You could tunnel Ethernet traffic over an MPLS network. You can tunnel even TDM traffic. You can do circuit emulation at the edge of the network and carry it as MPLS to the other part of the network. So it's already a very powerful concept here. Okay, now I will just mention this for now because we will use this in subsequent examples. There is the concept of label stacking in MPLS. And what we mean by that is, the examples I've given you so far imply that there was one label on a packet. But you can actually have multiple labels on every packet, just like you can have multiple .1Q tags. We call that label stacking. And label stacking is used for many things. One of them is when you're actually carrying a VPN packet. If you have a VPN packet, then you need 2 labels as a minimum. One label that gets you to the destination node, and the other label that tells you what to do once you got to the destination. That is called a VPN label. So in this case here, we have an example of a MPLS network where we've done some signaling using BGP MPLS. So this is one very popular application of MPLS. It's called BGP MPLS VPNs. That's defined by RFC 4364. So as part of that definition, in this example, what's happening is that PE2 and PE1 have created a VPN. And the two nodes that are part of it are CE1 and CE2. And what PE2 is telling PE1, I keep pressing the wrong button here, that for VPN-X, let's just call it VPN-X, please use the label of 1, 2, 3, 4. Right? So that's as simple as that. We will use that in subsequent examples. Just keep that in mind. The VPN label was 1, 2, 3, 4. Very simple label. Okay. So here's where things really get interesting. And you'll see how MPLS actually works as a result of following this example. Now, we spoke about labels, right? That a packet comes into an LER, and it takes the packet, puts a label on it. How does it know what label to put on the packet? The way it's done is by using a protocol that is called some sort of a label distribution protocol, a protocol that distributes labels. So one of those protocols is LDP, which stands for Label Distribution Protocol. So in this example, we'll see step by step how we build that incoming label map, which you will recall is the table that is used by routers to look up labels. Okay, so this example actually covers all of the concepts I've mentioned so far, but it does it in a sort of graphical way, so you can see exactly what is going on. A quick time check. All right, we're doing all right. So a network with 6 P routers or LSRs, 2 provider edges. We've got 2 CEs. CEs are just customer edge device. The customer edge device does not belong to the service provider. It belongs to a customer of the service provider. This domain is the customer's domain. You can see their loopbacks. They all have a loopback address in the 192.168.1 range. And we also see that all the IGP metrics are equal to 10 unless otherwise indicated. So this one here has a metric of 100 for whatever reason. It could be a low speed link, it could be a high latency satellite link, it could be a dial-up link. I mean, let's hope not, but it could be anything. But it's a slower link, so we do not prefer it. Okay. So what happens here is this. PE2 assigns a label for its loopback. Now, in an IP network, in a straight IP network, you would use the loopback to get to PE2, 192.168.2.22. In MPLS, we're using the label. So what PE2 does is it allocates a label from its label space, a label of 100. And it says, if I receive an MPLS packet with a label of 100, it belongs to me. So what I will do is I will strip the label. There is no out label. And I will process it locally because it's mine. It's destined for me. So PE2 does that allocation. What it then does is that it sends an LDP message to its neighbors. One of its neighbors is P3. So the message is saying, associate, now FAC actually stands for Forwarding Equivalence Class, in case you're wondering. It's just a fancy way of saying, no, this is the address. I will not worry about it too much. So just think of FAC as identifying the address, right? So that message is saying, if you get, it's saying, create a mapping for my address, 192.168.1.22, and that mapping should say that the LDP label that you use in order to send traffic to that address is 100, okay? So the message gets to P3. P3 then makes an entry in its incoming label map. That entry says that if I have to send anything to PE2, I use a label of output label of 100. And I send it on this interface, the interface to PE2. But now, P3 has to allocate its own label as well, because that's how MPLS works. So it allocates a label of 200. It says, I will use the label 200 to refer to PE2. So one key thing here is that these labels are locally significant. On every hop, we're using different labels because the routers could be using labels for many different purposes. So you cannot actually easily coordinate labels across all of these routers. We'll see that changes in segment routing. So P3 assigns a label of 200 and says, if I receive something with 200, I'll send it out on that interface to PE2 with a label of 100. That process continues. P3 now advertises. Now look at it. It's advertising a label of 200 because that's its label, its own local label for PE2. And P2 does the same. It allocates a label of 300, sends it to P1. P1 allocates a label of 400, it also sends it to P5, right? Because you're sending labels to all your neighbors. We haven't shown all of them here, just in the interest of saving some space, but it happens on all interfaces. You advertise the mappings on all interfaces. It gets to P1. So P1 now is interesting. Because what is PE1? Is it an LSR? Is it a PE or a P? It's a PE because traffic's coming in. So in PE's table, it is not a mapping of label to label. It's a mapping of IP address to label. Because what's coming from outside, or what it actually has to get to, is an IP address. So you'll see that the entry here is saying, if I have a FAC of PE2, then I put a label of 400 on it. Why do I put a label of 400? Because my neighbor told me to put a label of 400 on it for this prefix. So at the end of this process, every node in the network has a common understanding of what labels to use to get to PE2. And this happens not just for PE2, it happens for every node, right? I've just taken the example of PE2 here. So let's recap it. On this link, we used 100, 200, 300, 400. Simple as that. Easy numbers to remember. Okay? So is that clear to everyone? Does anyone have any questions? All right. I'll assume that we're all in sync here. So how do we use this information? Right? We've built the tables. Now traffic comes in. Traffic comes in from CE1. We know that CE1 is a part of which VPN? Remember, I spoke about it earlier. VPN X. So the first thing that this router does, it looks up the VPN label for the VPN that CE1 belongs to. And if you recall, that label was 1234, right? That was the VPN label. And I'll explain the significance of it in just a minute as I get to the end of it. But it looks up the label. The second thing it tries to work out is, where do I send this packet? CE1 and CE2 are part of the same VPN. So the packet needs to be sent to which PE device? PE2. So it looks up its incoming, or sorry, its label map there, the one we saw earlier, to find out what is the label to get to PE2. All right? And it decides that the label is 400, if you remember, right? It was 400 to get to PE2. So it pushes two labels. The label 1234 for the VPN, and don't worry about it too much now, but I'll explain. And the label 400. So now the payload looks, or the packet looks like this. You've got the, whatever the payload was. It could be an IP packet, or whatever it was, it could be Ethernet, but it's the payload. You put two labels on it. You first put this VPN label of 1234, and then we put the label of 400. The packet gets to P1. P1 needs to send it to P2. That's the shortest path, right? But the label that P2 is expecting is 300 for the same node, because that's what it told P1. That, if you have traffic for 192.168.1.22, use a label of 300. So what P1 does, it swaps 400 for 300. No change to the VPN label, just the top label. It goes to P2, does the same. It goes to P3, does the same. It gets to PE2. Right? Now here is the interesting thing. What we've done is we've managed to get the packet to PE2, because that's the destination for it, right? So the label that was put on the packet by P1, 400, designated PE2. So we managed to get to PE2. The packet gets to PE2. PE2 has to work out what to do with it. It pops the label 100. What's left? The label 1234. So it then uses the label 1234 to work out what to do with the packet. And it knows that 1234 is the label for VPNX. How does it know that? It knows that because it advertised that label to PE1. We saw that earlier, that MPLS BGP advertisement of 1234. So it knows exactly what to do with the packet. And so it routes it using information for VPNX within its routing table. Does it make sense? So for example, if you had 100 VPNs on PE2, they would all have a different label, a different service label for it. So this is the way it distinguishes between the different VPNs that are on that PE2. So for all of those VPNs, you would still use the same label on top. Now that label on top is called the transport label. Transport, because the job of the label is to get you to a specific node. And the inner label, or the one that's at the bottom there, is called the service label, because it tells you what to do once you've got to the destination. Yeah? Does that make sense? So that's basic MPLS forwarding using the protocol called LDP. Very simple, actually. It's not very hard to operate. So it pops it. It pops one. It looks at 1234, sends the packet out of C2. So MPLS forwarding really looks like that in general, right? We'll make some observations about LDP. Now, LDP is a protocol that follows the shortest path. So whatever we saw in the previous example, it was going along the shortest path. That means that we are not doing traffic engineering, which is, a major requirement in quite a lot of networks today. But it's simple. It works well. It scales really, really well. So it's not a bad protocol. The labels are always assigned by the downstream routers. So actually, that's a good point that I should probably go back. Right. When we look at this network, there are upstream routers and there are downstream routers. So the packet always flows from the upstream to the downstream. So the labels are assigned by the downstream routers. So always the downstream router is telling its upstream router what label to use. Because the label's coming into the downstream router, it needs to understand it. Okay? So the second thing that you saw is that the label changes at every hop. Right? Important concept. These are not globally significant. So they change at every hop. So keep that in mind. Okay. So very quickly, we continue our sort of rush through MPLS. There is another protocol that we use in MPLS that is called RSVP-TE. It stands for the Resource Reservation Protocol with Traffic Engineering. A bit of a mouthful, and it is actually a lot more complicated. Not just the name, but like the operation of LDP. LDP is a lot more complicated because it actually supports traffic engineering, as its name suggests. So I'll look at an example of signaling using RSVP-TE. And in your mind, try and sort of compare with what we saw with LDP. LDP was very simple. We just assigned some label mappings. Every node created its own label, advertised it. We used it. The network worked. With RSVP, a little bit more complicated. Same network, right? So here, what we do is a little bit different. RSVP actually signals end-to-end paths, whereas with LDP, we're just advertising label mappings of IP addresses to labels. With RSVP, we're doing a complete signal. The signaling starts from what we call the head end. The head end is the upstream router, okay? So it sends what we call a path message. This path message goes all the way to the destination. So it goes, as you can see, it's going to the destination. What is one thing that's different in terms of the path? Anyone? Is it the shortest path? Yes or no answer. 50% chance you'll get it right. It's not the shortest path, right? Because we're taking it over that link with a metric of 100. So that is immediately an advantage of RSVP-TE. It can let you build end-to-end paths that are not shortest path. And you might think, why? Why bother? Right? I want the shortest path. Because it matters, because the shortest path may not necessarily be the best path. It may be the most expensive path. It may be the highest latency path. So the metrics we have in IGPs to direct traffic may not necessarily be the most optimal. So in this case, in my example, I chose a non-shortest path, just to show you that it can be done. So it goes all the way to PE2. PE2 then allocates a label. So nothing happened until this point. So PE2 allocates a label. It says label 999 for this tunnel. Now this tunnel is actually called an LSP, or a label switched path, because we're building a complete contiguous path from the head end to the tail end. Okay? So it allocates a label for 999, and the operation it will perform if it gets a packet with a label of 999 is to pop it, right? Because it's the destination. It advertises it to router P6. Now, it uses a message called a ResV message, or reservation message. This message is what actually starts allocating labels, not the path message. The path message kind of kicks it off. As we go back with the ResV messages, it tells the routers what labels to use. So it actually follows the reverse path of the path messages. So it gets to P6. P6 assigns its own label of 888, and it creates an entry in the ILM that says anything coming in with 888, I send it out as 999. And so on, right? Goes to P5, P2, and they all assign different labels. So it ends up getting to PE1, and P1 has assigned a label of 555. So you see that the label it'll be using here is 555, 666, 777, 888, 999, right? So that's the path of the LSP that it'll take. Now, one key difference here between LDP and RSVP-TE is that if you built another tunnel now between PE1 and PE2, it would go through the whole process again. It would go through the path messages, it would go through the reservation messages, and would assign completely new labels. So the more tunnels you have, the more labels you'll use. The second thing is that all of these nodes in the middle here, right, P1, P2, P5, P6, have to keep state about every tunnel. They have to be aware of every tunnel. And that becomes a real issue with scaling RSVP-TE, as we'll see. So we look at the same example in terms of forwarding. This is something that should come easy now that you've seen the LDP example. So we've built the label tables. Packet comes in, we map it to that LSP, we push the VPN label, we push the transport label of 555. Put it on, get swapped here for 666, 777. So in terms of the flow of MPLS information and how packets are forwarded, it doesn't change whether it's RSVP-TE or LSP. The key factor here is the signaling involved in setting up these tunnels, okay? But the operation, the data plane part of it is exactly the same. The head end actually puts on the transport label. At every subsequent point, we swap the transport label to the one that is expected by the node that we are sending it to, the downstream node, the node that allocated the label. And then we make our way to the destination PE. There, it strips the top label, it looks at the service label, works out which service it belongs to, sends it out to that CE device. Is everyone clear on this? Any questions? Have I lost all of you? No? Okay, all right, good. I'll just assume that we're all good. So some observations on RSVP-TE. It's a bit like LDP. The label changes at every hop, but it's not like LDP in the sense that the more RSVP tunnels you have, the more state you are creating. And in fact, let me just go back to the last diagram here. So remember the LDP example where we had one label that was assigned by P2 for itself. It was labeled 100. Yeah, 100. So PE2 assigned a label of 100. And no matter what the source of the traffic is, they would always use that label to get to PE2. With RSVP-TE, you'll be assigned different labels all the time. So there is no one label for a node. It depends on the LSP. The more tunnels you create, the more the more labels you will allocate. So it uses up a lot of labels as well. The second thing is that unlike LDP, you have to explicitly signal RSVP-TE paths. If you haven't signaled the path, there is no RSVP-TE, there's no MPLS communication between the endpoints. With LDP, you do not do it that way. You just kind of turn it on, and it auto-discovers what's going on, and pretty much floods that information to the rest of the network. But with RSVP-TE, you have to explicitly go into the router and say, I want to create a tunnel to be 2. Create the tunnel. And so if you've got 10 nodes, you're going to be creating 45 LSPs. So a lot of LSPs that need to be created just for a small number of nodes. But why do we use it, right? It's not all bad. We use it because we can do traffic engineering. That is the one great thing about RSVP-TE, and that's why it's deployed in a lot of operator networks around the world. So I'm not going to go through this, right? You can see the pros and cons of the different label distribution protocols. BGP is also can also be used for label distribution. You saw that with the VPN. That label 1234 was actually advertised by BGP. So BGP can play a role in distributing MPLS labels as well. I need a drink. All right, quick time check. I think we've done all right. We're sort of halfway through it, which leaves us 45 minutes to cover segment routing. Now, I will be leaving basic MPLS at this point. So once again, any questions? Don't be shy. That's okay. Everyone's here to learn. No? All right, good. Then we'll carry on to segment routing. Before that. So we covered LDP and MPLS, right? But the requirement we have today is to do traffic engineering at scale. LDP does not support traffic engineering. RSVP-TE does, but does not scale too well. So what we want is something that gives us the best of both worlds. It gives us the traffic engineering capabilities of LDP and the simplicity and scale of LDP, right? And that's where segment routing came about, to just that. So segment routing is a technology that is defined by the Spring Working Group of the IETF. And really the objective of segment routing is to allow source routing. So you see the definition there. It says that it's the ability for a node to specify a forwarding path other than the normal shortest path that a packet will traverse, right? And if you can do that, it brings us a number of benefits. It can help with, network virtualization. It can help with different types of protection, such as node protection, link protection, give us fast reroute kind of capabilities. It helps with network programmability. I spoke about that earlier. Now, if you have a controller in your network, as in an SDN environment, that has a complete view of your network, that controller can provide information to source routers on routing packets because it's got a complete view of what is going on in the network. Not just a static topological view, but possibly a real-time view of traffic in the network, performance in the network, and so on. Couple of other things, simplification, reduction of network signaling. We saw that with RSVP-TE, we're doing signaling. We send a path message all the way to the tail. The tail sends reservation messages all the way back to the head end. And as they go along, they create state in each of the nodes. So the problem becomes scaling of what we call the midpoints, the P routers, the LSRs, because they're seeing a lot of LSPs, potentially all of them. They have to create a lot of state. And so we reach this point where we cannot scale RSVP-TE networks anymore. So that was an objective, right? So it uses source routing. And in segment routing, the source of the packet includes the routing information within the packet itself. So this is key, right? The packet includes information on how it is routed, and it's like I said, it's not, it's a bit of a foreign concept to us, because today we do hop by hop routing. Every router looks up the destination, makes an independent decision of where to send the packet. So we're moving from a paradigm where the router makes that routing decision to one where the packet is telling the router what to do with it. Quite a change. So the way segment routing has been defined is to actually use a couple of data planes. And what we mean by data plane is really how the packet is constructed and how it is forwarded in the network. So one of the data planes is MPLS, but there's also an an IPv6 based data plane, which is called segment routing v6, SRv6, where instead of using MPLS labels, we'll be using IPv6 addresses, right, to route the packet. So for the examples, as part of this tutorial, I focused on MPLS ones, but we can do a similar thing with IPv6. Okay, so with segment routing, the source determines the path a packet should take. And that source could be instructed on this path by a controller, right? But one way or the other, the source has knowledge of what to put in a packet. And it puts in the packet a sequence of segments. Now remember I said a segment is like an instruction. It's like topological information, what node to go to, what interface to go out of. So two types that we'll look at as part of this tutorial are node segments. A node segment is a label that identifies a node. And then there's an adjacency segment, which is a segment that identifies a link, right? And those are the things that we typically need in a network, right? IP networks are made of routers and links. So with the combination of these two things, we can actually construct some pretty complicated paths in an IP network. So the source puts that information in the packet, and intermediate hops between the source and destination just look at that information and route the packet based on it. The most important thing about segment routing is that these intermediate hops do not maintain any state on a tunnel by tunnel basis. It's called global state. It does not have per path state. So you can have many paths, but all of them share the same tables, all right, of global information. So few different use cases. One use case for segment routing is just like a standard shortest path routing. So this is not really getting any real benefit of traffic engineering. What it's doing is it's just doing standard shortest path routing. Because, you know, not all traffic needs to be traffic engineered. Some does need to be, you know, routed using shortest path routing. So that's one use case. Where, okay, so this is just showing you an example of a MPLS VPN where we've signaled, where P2 has signaled using MPLS BGP VPNs, right? So using MP-BGP, a route for Z within VPN X, which has a label of LZ, and it says my next hop is P2, all right? So that's just one. And what you want to do is you just want to send the traffic down the shortest path. The other use case is for what we call fast reroute, where what we'd like to do is build highly resilient networks that converge very quickly when there is a failure of something, a node or a link. And typically in MPLS environments, we talk about rerouting within 15 milliseconds. So the intent here is that you build a tunnel between the source and the destination, and at the same time, you also build other tunnels that are there in case any nodes or links within that path fail. So that when there is a failure, you quickly send traffic on these alternative paths, the backup paths, so you do not lose a lot of traffic. And the requirement is usually to do it within 50 milliseconds, right? So pretty rapid rerouting. So that's one. And then there's traffic engineering. So traffic engineering is complex. There is a lot to traffic engineering. And you know, the whole point is to have more control over your traffic. So for example, you could be running a network where you're providing services to different types of customers. There could be your residential, you know, broadband customers. There could be enterprise customers. There could be banks and so on. And they all need a different level of service. They have different SLAs. So one could be that, you know, one objective of traffic engineering would be that for your best effort residential internet traffic, you put it on your best effort path, your shortest path. But for your more critical, higher paying customers, you put it on the lower latency paths, back it up with you know, fast reroute, backup tunnels, and so on. So traffic engineering comes in useful for a lot of this. But the way we do it is also quite complicated, right? We can specify traffic engineering in many ways. So you can explicitly specify every single hop you need to go to. That's one way of doing it. The other one is where you partially specify it. You say, hey, I want to go, router 1 needs to go to router 3. I don't care how it goes there, but from router 3, it has to have a direct path to router 4. So you can combine a couple of these, what we call loose hops with strict hops. It depends on your requirements. So there's a few things that we can do there with traffic engineering in terms of how traffic is routed. Okay, so that was a bit of theory. I want to go back to an example to show you how things change in a segment routing world, because it's important that you understand that concept and how it is different from typical LDP or RSVP-TE based MPLS label distribution. So the first case is the shortest path case. So this is emulating what we can do with LDP today, right? That first example that we had with LDP. So what we're saying here is that the use case is an ECMP-aware shortest path routing. Now, the reason we say ECMP-aware is that in this kind of a network setup, you want to exploit parallel paths. So if you have equal cost paths, 2 or more equal cost paths, you want to be able to use all of them, right? Spread your traffic across all of these equal cost paths. And so, you know, in a shortest path routing environment, when you have two paths that have the same total metric, then you load share over them. The second thing here is saying that we will be using segment identifiers as node SIDs only. Now remember I said that there's a few different types of these. There are node SIDs that identify nodes, and that there are adjacency SIDs that identify links. In this example, we only use node SIDs, just to simplify things. And we have this concept of an sRGB. I haven't really introduced this concept, but just quickly, the sRGB, or sRGB actually stands for Segment Routing Global Block. What it is it's just a block of labels that are reserved by routers. But the key change in segment routing is that this block of labels is intended to be globally significant. If you recall, with LDP, every router assigned a different label. With RSVP-TE, every tunnel had a different label on every hop. With SR, a key change is that these labels are globally significant. So in this example, all of the routers are using the same global block of labels to allocate labels for segment routing. Okay? So let's look at this. Similar sort of network to what we had before, just to keep it simple. But a few more bits of information. Now the first one is the segment routing global block that I just mentioned. So you look here, you see that all of them have a block that is 100 to 499. So this is part of the MPLS label space. So all of these routers have set aside 400 of these labels, from label 100 to 499 for segment routing. The second thing is that all of these routers have been configured with a SID. A SID is a segment identifier. And this is a node segment, as I mentioned before. So this SID uniquely identifies this node to the rest of the network. So they have to be necessarily unique, right? So you see that P1 is 101, P2 is 102, P3 is 103, 104, 5, 6, and P1 and P2 have their own SIDs, 111, 222. So we've done the basic setup here, right? Now we look at what happens from a control plane perspective. Okay, that's the use case. The objective here that we have is to deliver traffic between P1 and P2, right? In fact, at the end of the day, that's all we do, right? I mean, when we build networks, deliver traffic from point A to point B. We just find new ways of doing it. So in this case, traffic between P1 and P2 via the shortest IGP path, which will be this one here, the top one, because this is too big, right? This metric. So that's the path that we want traffic to take. Okay. So we have to build the incoming label map. Now, previous two examples, the standard MPLS examples, used protocols. They used LDP. So remember, LDP sent a label mapping message between the FAQ and the label. We used RSVP-TE. RSVP-TE used path messages, reservation messages to advertise the mapping between the IP address and the label. Segment routing does not require LDP or RSVP-TE. So that's one benefit of segment routing already, in that we do not need another protocol to do the label distribution. But we still need to distribute the labels, right? The nodes have to find out what these SIDs are, the SIDs that we've assigned. So what's being done for segment routing is that IGPs, so OSPF and ISIS, have extensions now for segment routing that allow these protocols to advertise mappings between the node addresses and the segment identifiers. So in this case here, PE, whoops, what am I doing here? Right. PE2 associates SID 222 with its loopback of 192.168.2.22. It then advertises it via its IGP. Let's say it's ISIS, right? It advertises it to the rest of the network. So it gets to P3. P3, when it gets this message from ISIS, which indicates the label for PE2, creates an entry here in its incoming label map. Now you see, here is the big difference between what we had in LDP and RSVP-TE. Because in LDP and RSVP-TE, this outgoing label would be the one used for PE2. And the incoming label would be assigned by this node. In segment routing, these labels are globally significant. So the incoming label is the same as the outgoing label. All nodes in the network will use the same label to reach PE2. So you can see how that simplifies things. That no matter where you are, you know what the label for PE2 is. So it creates a mapping that says, if I receive a packet with a label of 222, I swap it for label 222. Now, even though the label is not changing, the router still performs a swap operation, right? That's MPLS, right? That's the nature of the MPLS data plane. A MPLS labeled packet comes in, the router will look up the incoming label in its ILM, work out where to send it and with what label. So by keeping this, we can reuse the MPLS data plane, the hardware, the software that is out there today that does MPLS. So segment routing kind of has extensions to the control plane, but it uses the data plane, which is very powerful, because every time you introduce a technology that needs a new data plane, then you need new hardware, right? So as you would recall, like IP routers that supported IPv4 may not have supported IPv6 in the hardware, right? Because, or at least with the performance that you had with IPv4, because it needs to switch this in hardware, and it's got to have the capability. So reusing the MPLS data plane means that we do not have that challenge. Okay. So we move on, and I've lost my point. Oh, here it is. That happens to all the nodes. So can anyone tell me what the ILM entry in P5 is going to look like, or P1, or P4? Exactly the same. Yeah, that's right. All of them will have the same ILM. You can already see how it becomes simpler, right? So P5, P4, you name it, all of them have the same ILM entry. Anything coming on 222 is swapped for 222, and we know that it goes to P5. So a lot simpler for a shortest path application, right? Remember that this label is the transport label. You put the label on a packet, it gets to the destination that it corresponds to. Okay, so we build the table. we do the forwarding. Once again, a lot simpler. Packet comes in from CE1. PE1 puts on two labels. It puts on the VPN label, that's always there. For our examples, may not be there, for your application. And then it puts the transport label, because it's got to get the packet to PE2. It looks up its effect to label mapping, and it says, PE2 is label 222. So it keeps going, goes to P1, that's the shortest path, gets swapped. P2 gets swapped. P3 gets swapped. P2, it finally gets to its destination. P2 pops the label, looks up 1, 2, 3, 4, sends it to C2. Does that make sense? Any questions? So it's pretty simple, right? It is a lot simpler than LDP. Well, okay, no, I wouldn't say a lot simpler than LDP, but definitely simpler than RSVP-TE. So great. So if we just did this, what have we achieved? If we just did segment routing for shortest path first, what have we achieved? It does exactly what LDP does, except that it uses globally significant labels. But it doesn't require LDP, right? It's an extension to the IGP. So, okay, so one benefit here is that you've got one less protocol to deal with, right? Instead of maintaining LDP and OSPF and ISS or whatever it is you're using, you've just got your IGP. So there are already benefits of using segment routing for shortest path first. But that's probably not enough. The real power of segment routing comes when you do traffic engineering, which is our next example. Okay. So the same topology, but the example is an SRTE example. So we specifically say SRTE when we mean segment routing with traffic engineering. And there's obviously quite a significant difference between doing shortest path with segment routing versus doing traffic engineering with segment routing. So it's the same example as before. We have the link, if you remember, there's one dodgy link, right, that has a metric of 100. What we want to do is we want to build a path between PE1 and PE2 that goes between, that goes over the link that has a metric of 100, which is something that we cannot do with shortest path routing because that would not be the shortest path. So for whatever reason, we've decided that's a good path for this traffic. Now in this case here, we use both node segments and adjacency segments, okay? Because we have to, and I'll show you why. Okay, so same topology, as you see, all metrics are 10, that one's not. Objective, traffic from PE1 to PE2 should traverse P2. So there's the other condition that I want all my traffic to first go to P2 and then it should go to PE2, but it should not use this link. Right? Now this is arbitrary. I've just made this up. In your network, you might have a good reason. You might have a good reason to send it to P2 because it's cheaper or faster or better or something. Whatever reason. I'm sure there are lots of reasons for traffic engineering. And there could be reasons for avoiding the P2 to P3 link. Like I said, it could be a high latency link, or it could be a very expensive link. You want to reserve it for, like, your highest paying customers. And this traffic is best effort. Doesn't really matter, but this is what we want. So question, can we do this with the IGP? Can we force traffic like this with the IGP? No, we can't, right? We can do policy-based routing. You can do stuff like that. It's not simple, and it's it's kind of error-prone. So there are no really good ways of doing this. If you just stuck to your normal IP routing capabilities. Segment routing offers you that opportunity. Okay, so let's do this. So what we want to do here is really use the concept of source routing, right? Remember what I said. In source routing, the information on how to route the packet is put in the packet itself. Think about the previous example. Did we do that? Did we put information on how to route the packet in the previous shortest path example? We didn't. We put one label on it, 222. That label is just the destination. So in the shortest path routing paradigm, we're just telling it the destination and letting the network take us to the destination. With traffic engineering, we go beyond that, right? So what happens here is the payload comes in and PE1 puts a whole stack of stuff on the packet, right? And you need to pay attention to what this actually means. So in the previous example, we had this. We had payload. We had the label for VPNX. I haven't used actual numbers here just to make it a bit clearer, but these will all be numbers. This will be labels, right? So in the shortest path example, this was VPNX 1, 2, 3, 4. And then we had the label for PE2, which was 222, right? But in here, we've got a lot more. Because this part here, from node PE2 upwards, is giving you complete routing information on how the packets should be routed. Now, one thing that I probably did not mention earlier is that when you have a stack of labels on a packet, when it gets to a node, it always looks at the top label, okay? It doesn't look underneath it for the purpose of switching. It always looks at the top label. So we start off here with a label for P2. That P2 is the SID for P2. Does anyone remember the SID for P2? What was it? It was 102, I think. Sorry? Segment ID for, yeah, okay, yeah, so the segment ID for P2, I think the number was 102. We won't use it, but it had a SID. And that number stays the same, right? So what we do is, firstly we put a SID for node P2. And let's just say that's 102. Then we put a SID for node 5. We then put a SID for the adjacency, right? The link. Whereas the previous identified the node, this one identifies the link between P5 and P6. And then we put, finally, the destination, the node P2. So what does it actually mean? What is it telling us? What it's really telling us, and the way to read this is, we are putting information in the packet that is telling the network that, you know what? Send the packet first to P2 through the shortest path available, right? So, you know, PE1 has two ways to get to P2. It can go this way, or it can go that way. But the top one is the shortest path. So it says, get the packet to P2. Once it gets to P2, then send it to which node? P5. We have to force it because we're saying we do not want to use this link, if you remember. So we say, send it to P5. Once you get to P5, it's saying, send it over the link between P5 and P6. So it has to send it over this link. We cannot say at this point, send it to P6 only. Because if it did, it would take the shortest path. And the shortest path is this way, right? Because that's a cost of 10, 20, 30, 40. And this is 100. So we have to explicitly force it down that adjacency. Once it gets to P6, then we're saying just send it to P2, which happens to be directly connected to it. So the key thing to take out of this, we're putting complete routing information that impacts the path into the packet. This is like in an IP network, putting a list of IP addresses and saying, hey, go to this hop first, and then go to that hop, and then that hop, except we're doing it in the MPLS label. So let's see how this works. So it sends it, it sends it to P1. P1 looks at the top label. What is the top label? Node P2. it will have an entry in its ILM, remember? That says, anything I receive with a label of 102, I send it to 102. Because we're swapping the incoming label for the same outgoing label. Every node will have a unique label. So it'll take the label for P2, replace it with the label for P2. It gets to P2. The top label belongs to P2. It pops it because it's there. You've made it, right? And then P2 looks at the new top label, which is P5. And so it knows that the way to get to P5 is the direct link. So it sends it to P5. So we've achieved the first step. What was the first step? We want to get the packet to P2. We've done that. Next step is to get it to P5. It cuts to P5. P5 looks at the label and he goes, that's my label. I'll strip that. It strips the label. So we achieved the second thing, which was to get to P5. At P5, oops, let me just step back. P5 strips the top label and then looks at the next label, which says the adjacency between P5 and P6. And it knows about that adjacency. So it strips that label and it sends the packet directly over this link. So it's taken off the last two labels, or the top two, the node P5, P6, leaving it with a label of P2. It gets to node P6. It looks up the label for PE2 in there. And it knows that it's got to swap it for the same label, PE2. Sends it to PE2. We've finally made our way to the destination. PE2 strips its own label, looks at the service label of 1, 2, 3, 4, and then it routes it to node CE2. Does that make sense? Do I need to repeat this, or did everyone get that? So do you see the power of segment routing? We are able to route the packet on a totally arbitrary path. We said we want to go to P2. We said we'd like to avoid the link between P2 and P3. We want to go to P5, take the link between P5 and P6, and that's how we get to the destination. So question is, how is this different from RSVP-TE? Because we had the RSVP-TE example, if you remember. Was it exactly the same in terms of the path? It was the same path. So we can do this with RSVP-TE. So what makes this better? Why would you do this? The answer is that there is no signaling. With RSVP-TE, if you recall, I said there's signaling. There's a path message, there's a RSV message. Every node in the middle has to understand that LSP's route. So in the case of RSVP-TE, you create the tunnel on P1. P1, P2, P5, P6 have state about that tunnel. They have to understand that there is a tunnel going through it. P2 has to have state. In segment routing, no router has state on the tunnel except PE1, because we are using globally significant labels. So if you create it, so it's not tunneled, and the reason it doesn't have state. The reason it does not have state is because all the information that these routers need to route the packet is in the packet itself. So we've taken the state that was in the router, moved it to the packet now. And that means that we can really scale the network massively compared to what we could do with RSVP-TE. If you created another tunnel, and by which I mean you had a different set of labels here, or even a similar set of labels that touch the same parts along the way, they would still be using the same set of labels to refer to the destinations. Whereas with RSVP-TE, you'd be assigning completely new labels all the time for every new tunnel. Here, being globally significant labels, we end up using the same label over and over and over. So the size of the ILM, the incoming label map, on each of these routers is actually quite small. It's actually the size of, or it's actually the number of nodes in the network plus the number of links on that particular router. That's it. So it scales really, really well. So that's the benefit of segment routing traffic engineering, in that we can do some really fine-grained traffic engineering without killing the network. Okay. So we've kind of covered what I wanted to, at least as a minimum, because I wanted you to understand how the signaling happens in terms of the mapping of IP addresses to SIDs. Once it's done, how the ILM is populated, and then how is traffic actually forwarded in the network. So we've got a few minutes left, so what I'm going to do is I'll quickly go through architecture, and then maybe leave 5 minutes for any Q&A if you do have any questions. Okay, so in terms of architecture, we've already spoken about this. Segment routing allows us to steer packets through a set of nodes, depending on what information is put in the packet. It doesn't require per flow state. Okay, we already talked about that. You saw what a segment is. A segment is, so I hope that demystifies the whole concept of a segment. Because when you hear a segment, it doesn't mean anything, right, by itself. But think of a segment as just a node or a link. And a segment routing packet has information about nodes or links that you wish the packet to go through to get to its or on its way to the destination. Segment identifier. Now we looked at MPLS examples where the segment identifier was an MPLS label. It can get a little bit more complicated in the sense that if we have environments where you have equipment from different vendors and they do not all support the same segment routing global block, you can use different segment routing global blocks, and instead of using an absolute MPLS label value for a segment identifier, use an index into the global block. So then the requirement becomes that the index has to be globally significant as opposed to the label value, because you have different sRGBs. But don't worry about that too much. Okay, that's one. The other one is that, as I mentioned, the SID can actually be an IPv6 address. The challenge, of course, is if you go back to my example, SRTE example, where I had, how many labels did I have on it? A lot of labels, right? And each IPv6 address is 128 bits, as we know. So the size of the header could get pretty high, pretty big, right? Okay. Segment list, we've already spoken about, so I'll skip that. Segment router global block. I'm just rushing through it so I can get to some of these. Okay. So in terms of segments, these are all in the slides that you can download. You'll see that we've got IGP segments. There are also BGP segments that exist, because you can do this for route selection for traffic that is leaving your network as well. Things called egress peer engineering. But we have global segments, and we've got adjacency segments local segments. So the adjacency segments, the ones for the links, are not globally significant. They're advertised globally, but they're significant to the node itself. And in terms of the global segments, which are what we call prefix SIDs, you've got a few types. You've got node segments, which we looked at. We've got anycast segments as well, and there are things called remote binding segments too. It gets a little bit more complicated once you start interworking with other protocols, with building inter-AS systems and so on. Skip that. Okay, so MPLS data plane. We saw that in segment routing using the MPLS data plane, the segment is encoded as an MPLS label. So, the reason we can do this is because MPLS already has this capability for label stacking, which means that, like I said, it's very easy to introduce this into an existing MPLS network because the only changes required are control plane changes. So you have to enable the extensions for segment routing within your IGP, but then your data plane remains exactly the same. The active segment is always the one on top. The top label is the active segment that we look at. The sRGB, so we looked at that, right? So in my example, it was from 100 to 499. But in typical networks, the MPLS label space goes from 0 to 1048575. And so you'd carve out a block of it for use as the sRGB. In this case, we're using about 16K of these. So I might actually skip this. Yeah, I might actually stop at this point. Okay, so we've kind of covered some of this. I know it's a pretty quick rundown of segment routing. So as part of this tutorial, I started off by giving you a bit of an introduction to MPLS. For those of you who are not familiar with MPLS, for those of you who are, that would have been pretty sort of simple bread and butter kind of thing. But the key point was to illustrate the way the control plane protocols work with traditional MPLS implementations. We looked at LDP, RSVP-TE, and the fact that there are challenges, right? I mean, there are always challenges. There's no such thing as a free lunch in networking. We know that, right? You increase something here, something goes down somewhere else, right? It's all a balancing act. There are trade-offs. And we saw that LDP is simple. It can scale really well. It's so easy to configure. If you went to the SDN workshop, you would have seen that. Just turn it on. It works like magic. It just works. But it's only shortest path first. You cannot do traffic engineering. It's called fast reroute. You can do fast reroute with it. You don't always get full coverage, but you can do it. So it's it's not a bad protocol. But if you want traffic engineering, you'd have to do RSVP-TE. RSVP-TE is complex. Every tunnel has to be built. It has to be configured. It can be there are mechanisms to automatically create some of these tunnels through capabilities that are provided by different equipment vendors, but they still need to be created one way or the other. And it ends up in a situation where if every node in your network needs connectivity to every other node, then you have an n-squared meshing problem. Now this is a non-trivial problem to solve because you want reachability between all points. So how do you do it? So if you create this full mesh, you end up with lots and lots of tunnels, and your network will reach a point where it kind of gets capped. You cannot go beyond it. There are techniques to get around this, right? We can tunnel LDP over RSVP-TE and so on. So building hierarchy of LSPs, but they're not the easiest to manage. So with SDN and the more on-demand nature of network connectivity, what we want is finer-grained control, where we want to do traffic engineering on a per application basis. For voice traffic, for example, or interactive video traffic, you might want the best routing in your network. For just internet downloads and things like that, for web browsing, maybe not. So we want to create this differentiated behavior in our networks, which means that the problem of n-squared meshing becomes even more compounded. There's an explosion of connectivity requirements with different routing. Very hard to do in a scalable manner. So with segment routing, we see that what we can do is we can move some of the decision making to a central controller, as in an SDN controller, and this SDN controller then has the intelligence to be able to derive these paths and push that on to your source routers, your head ends, and then these head ends do not actually have to do any complex computations. They just have to put this information in the header of the packet. And then through the network, the packet is routed as per the instructions in the header of the packet. So really powerful mechanism. So we see that a lot of operators are implementing segment routing in the networks today, with some of the operators that I work with who are doing 5G or implementing the first 5G networks. They're using that as an opportunity to implement segment routing in the networks. So it's a very interesting new paradigm. That's kind of all we have time for. If we have any questions, I'd be more than happy to answer them. Anyone? Yes, please. Do we have a mic? Or, do you want to come to the mic, please?
I'm Susu Win from Myanmar. Your explanation, LTP, RSVP, and traffic engineering was very clear and very cautious for me. I very well understand very well. And I would like to know one thing is you said data plane and control plane is a hardware requirement, a little bit detailed explanation, and next thing is 5G in segment routing, link refer or anything. Another one is router pen testing. I would like to know a little bit.
So sorry, so what's the second question? The
5G in segment routing.
5G segment routing? Why are we doing segment routing 5G?
What can I do for the 5G in segment routing?
Right, so with 5G, one of the things in 5G is that 5G is a more distributed deployment, right? With a lot of the core elements of 5G are now cloud native. They're sitting in a virtualized form, and with some of the requirements of 5G, such as low latency services, operators are starting to look at building edge clouds. So they push content into virtualized environments at more distributed locations. So in a cloud environment, what we have is we have dynamic instantiation of service. So for example, you could be let's just say that there is there's some sort of event, and as a result of that event, you're expecting a lot of traffic on a certain service. Then with NFV and virtualization, you have the ability to now spin up some servers on demand to handle the amount of traffic, right? And then when the traffic is gone, to tear them down as well. So what we see here is that when you turn them up, now you have a lot of traffic going to it. So you want a network that reacts dynamically to it. So having segment routing traffic engineering means that you can now create these tunnels to go to these new service. When it's gone, you can tear that down as well. So there's a need for dynamic traffic control, which is required by 5G, which segment routing is well suited for. Okay. Any other questions? Okay. Well, look, I do hope that was useful, helpful. If you have any questions, I'll be here for the rest of, most of the day. Yeah, and so. Be more than happy to have a chat with you offline. In the meantime, thank you very much. Thanks for attending my session here. Appreciate it.